I work with Professor Ignacio Araya, he's here, and also with Georgios Anastasio. So they both are my co-advisor. So this is some recent progress on digital holography regarding quantum information aspect of this digital space. So to start with, which you can click the yeah. Yes, so I will just give the outline of my talk. So first I will talk about what is quantum entanglement and some related measures to understood the entanglement between systems. And then I will talk about how to introduce those things to quantum field theory to continuous limit. And then the holographic calculation of those quantities using the dictionary of holography. And then our work on shape deformation of subregion in the digital space, and then I will conclude. So yes, so what is entanglement? And so entanglement is a quantum phenomena between two subsystems, or let's say more than two subsystems, which is like a relation between subsystems, but quantum mechanical relation. So for example, if I take two spins, like spin 1, spin 2, and I define a state called Bell state with this. So one for spin A, let's say it is up, and spin 1 half, so it has up and down two possible states. And for spin 2, it is down, and then the combination is such that for the other part, it's the opposite. And this is called the maximally entangled state. And for this, you can see that you cannot write the total Hilbert space as a direct product between Hilbert space for A and Hilbert space for B. So that's why when you cannot write like this, you can say that both the systems are correlated quantum mechanically, and that is quantum entanglement. And one of the major, or let's say the important measures of quantum entanglement is what is known as entanglement entropy. So I will talk about this entanglement entropy. So as I am saying, if you have a system with two parts, A and B, so we say that these are subsystems in between the whole system. Then if you define a pure state for this whole system, let's say with states psi, then you can introduce what is called the density matrix for this state that is given by this bar psi get psi. And then I divided this whole system into two subsystems, A and B. So Hilbert space is divided on HA cross HB. And then you can introduce a notion called reduced density matrix for particular subregion, let's say for A or B. To do that, you have to sum over all the degrees of freedom on the other half. So if you want to calculate density matrix for A, you have to sum over B. So that's why I have taken trace over B. Or for B, you have to then take trace over A. Once you do that, you can define a quantity which is a von Neumann entropy, or the quantum version of Shannon entropy, that is defined by minus trace of rho A log rho A. And this is called the entanglement entropy. And as rho A can be diagonalized in matrix element, so here I am talking about like discrete system like quantum many-body or two-spin system like that. So you can write it in terms of eigenvalue with the lambda I. And then SA takes this simple form, that is summation over I lambda I log lambda. Why this is important? Because I can show you some example using this derivation. So ultimately, what is entanglement entropy giving us is this, that the amount of correlation between A and B, or the amount of entanglement. And if it is in a pure state, the whole system is in pure state, then one is the important property of entanglement entropy is that the entanglement entropy for A and entanglement entropy for B are same. Yes?
Yeah, I have a question. In the previous slide, you said that yeah, that one. Yes, that the spaces can't be split.
Yeah.
Right? But then on the next slide, you're kind of splitting it.
Yeah, so this is the like splitting of Hilbert space. It's not splitting of state. So here the state is like a direct product. Like you can separate all this, like all the information of A multiplied with all the information, like psi for A and psi for B. That is not like separating of Hilbert space. In Hilbert space, you can have such a state where you cannot write as a direct product. There may be correlation. That's what I'm saying. So there can be complicated. Like another example, I will show you where there is no correlation. So yeah, I will show you in the next slide. So here we will understand here. So here, if you see, I have defined this state for the whole subsystem, whole system, where the S spin is on ground state and B spin. Okay, yes, perfect. So and for the S state, it is like up and down, and then product with B with up and down. So if you do that, you can see that you can easily write it as a psi of A cross psi of B. So you can separate two subsystem total. In that case, if you calculate the entanglement entropy, you see that it is exactly 0. Because if you take summation over this, you see this give you 0. So it is not entangled. But in case of this Bell state, as you can see here, you cannot write it okay as a like a simple state for A cross simple state for B. So for that reason, in this case, you see that entanglement entropy is log 2, which we call the maximum entanglement. So in both cases, you can separate the Hilbert space, but in one case, you can write it as a direct product between two subsystems, but in other case, you cannot write it. So that's the difference. Yes. So now, as I am saying that this entanglement entropy is a quantum information measure. So how we understand entanglement entropy from quantum information perspective. So this is super interesting for like quantum computing and other thing and quantum teleportation. That is so, as I am saying, you have the whole system, but I have like one part which is A and other part is B. Then, as I have said, you can like divide these two systems like HA cross HB. So this is the Hilbert space. Then one thing you can do, what is called the local operation. Local operation you can do in a particular subsystem. This is a quantum mechanical, like a measurement kind of thing. So you can do quantum mechanical operation into a subsystem. I am calling it LO, local operation. So you can do projection measurement. Means in quantum mechanics, when we probe a system, we basically do measurement, because if you do quantum measurement, you can change the state of a system, or you can do like other quantum mechanical operation, like operating with a gate or operating with other quantum mechanical thing. So I am saying that is as a local operation, but that is only restricted to A or B. So you can do partwise, but you cannot extend between them. And then the other part is classical communication. So for classical communication, let's say I have separated A and B far away. So let's say A is in Earth and B is in Moon. So then you want to communicate between these two using classical information. Let's say by emailing or by phone call. So you do some measurement in A and you call and inform it about the outcome of this result to B by a classical communication. So altogether, this is called LOCC. So local operation and classical communication. One of the basic example of this is quantum teleportation. So using this technique, you can do quantum teleportation. Why I am telling this? Because I will use this for the next slide. So as I am saying that A and B are highly quantum mechanically correlated. So you don't know what is the quantum information scale. But what you can do LOCC. So you can do some quantum mechanical measurement in A or B, and then you share the information between A and B. Once you do that, this process is called distillation. So you are kind of distilling the whole system. Then you will see that A or B now are simply a relation of Bell pairs. So let's say there are M Bell pair here or N Bell pair here, and you can see that this complicated correlation become just simple number of Bell pairs. And for the perfect measurement, I am taking like a M copies of the system. Instead of taking a simple 1 copies, I am taking M copies for statistical improvement. Once you do that, you can show that this n copies of your initial entangled state is now like n copies of Bell state. Once you do that, you can take n going to infinity limit. So like infinite number of copies of the system, and you can see simply that this n by n, see the number of Bell pair divided by the number of system you have. So that will give you a number of Bell pair for a single system. That's what we wanted to know. And if you see that will give you exactly the entanglement entropy for a system. So what we understood from this is basically that the entanglement entropy is nothing but the number of distillable Bell pairs between two such systems, A and B. So this is quantum information aspect of this thing. Okay, so after understanding entanglement entropy, we can easily ask, like, is there any notion of another measure for entanglement? And the answer is yes. You can define a new measure called pseudoentropy, which is kind of a generalization of entanglement entropy. But what you do, you basically change the state. So if you see, when I was describing this one, density matrix, I have taken psi bar and ket psi, but both are same state. So initial and final state are same. But for pseudoentropy, what we do basically, we take two different states. We take initial state psi and other state phi. Once you do that, you can then define what is called the transition matrix, because you no longer have same state. So the transition matrix is defined like initial state and then the final state. And then I have taken the like a normalization factor. So this is transition matrix. So then you can follow the same step. We have done it for pseudoentropy. We can define the transition matrix for a sub-region. So to do that, you have to take trace over B. So this is called the reduced density matrix. And then you can define similar to entanglement entropy, but now it for the transition matrix instead of density matrix. And this is called pseudoentropy. So some properties of pseudoentropy is that in general, this transition matrix can be non-Hermitian. So if it is non-Hermitian, it can be complex. So if you take the trace of this one, so if this is non-Hermitian, the S can become complex. And if either of the state is in a product state, when you can separate the two states, then the entanglement, pseudoentropy simply becomes 0. So there is no entanglement if the state is pure. Like you can separate psi and phi. And then there is a conjugation symmetry if you exchange the state. So if you change the initial state and final state to final state and initial state, you have to dagger it, because in general it can be complex. And then the equivalence same holds for pseudoentropy, what holds for entanglement entropy, that the subregions entanglement entropy are same. So the pseudoentropy for A and pseudoentropy for B is same for pure states. And finally, if both are same, the initial and final state are same, they reduce to the well-known entanglement entropy. So basically, that's why it's a generalization of entanglement entropy.
Sorry,
Yes.
that transition matrix is somewhat related to the transition matrix in a having event.
It's like any transition matrix. Like if you have two states, you can always define a transition matrix. It can be any system. So it's very like a generalized definition. You can use it for any kind of system if you have two states. So it can be discrete, quantum field theoretic, or other kind of system. What you need basically is that these two states are non-orthogonal. If they are orthogonal, then this will become 0, right? So then it will be undefined or not well defined. So that's why if they are non-orthogonal, you can define this transition matrix. There is no problem.
Question?
Yes.
Why do they have to be non-orthogonal?
Because of this, right?
Not because that it's like a consequence of them not being non-orthogonal. Like I guess, can I have a system that has all spins up, then all spins down, calling that like a pseudoentropy as well?
I don't understand. If you are
You're taking an initial and final state
Yes.
of the system. Okay? So I can have an initial and final state that's orthogonal or not?
Yeah, you cannot have, because by this definition, right? Because if they are orthogonal, the inner product will be simply 0, right? If two states are orthogonal, then this will become 0, so the whole quantity will become infinite.
I agree. But is there like a principle that states that both states do have to be orthogonal or do not have to be orthogonal?
No, there is no principle, but to define a transition matrix like we are defining, because you see, it have to give you total, total, what is like trace of this. Like if you want that total, how to say? If you do any measurement, you know that total probability should be 1, right? Like in probabilistic theory. So any statistical mechanics or any probabilistic theory, the total probability should be 1. So to do that, you have to use this normalization such that after summing, the total probability should be 1. So once you want to do that, you have to multiply with this normalization, and once you do that, you see that the constant is that whenever they are orthogonal, this state is not well defined, the quantity is not well defined. So this is the restriction. There is no physical reason why you are restricted to that, only that you should add up to 1 to get the correct probability. On the path, you have this restriction. So there is no physical reason why you should. Okay. So now we can ask the following: does pseudoentropy also have some quantum information aspect? Because we see that for entanglement entropy, we do have some quantum information aspect, that is the number of distillable bell pair between A and B. Then you can ask whether pseudoentropy also have this number of bell pair between A and B. And what we have found that for all kind of transition matrix, it is not possible to find quantum information space. Only for particular class, for what we are calling class E, where the transition matrix are Hermitian and semi-positive definite. For those cases, you can see that the pseudoentropy is equal to number of distillable bell pair between A and B. So for those kind of transition matrix, the quantum information LOCC interpretation still holds, that you can recover the number of distillable bell pair. I have given a simple example. So if you take psi to be cos theta 1 and sin theta 1, this one, and phi to be, so these are two different states. And then you can calculate the reduced transition matrix, and then you can see that the number of distillable bell pair m is basically m times the pseudoentropy. So for this class C, it is correct that you have a quantum information like interpretation of pseudoentropy. But you can say then, if I want to define a quantity which will always give you like quantum information measurement, then there is this SVD entropy, which is like a generalization of this pseudoentropy, but for real setting. So what you do is basically you take mod of this transition matrix. So I have told you that this can be complex. So what you do is basically you take the transition matrix and conjugate with its conjugate, and then you take square root. Once you do that, you will only find the real quantity. So once you define this real quantity, you can define the von Neumann entropy associated to this quantity. And in this process, this SVD entropy is always real and can be interpreted as a number of distillable bell pair between these two states. So that's why we can define this SVD entropy. Okay, so now the relevance of this SVD entropy is following. So we can use it for post selection. So means if you start with a state and you can go to a different state, then you have to define pseudo entropy. Or if you want to use tensor network or temporal entanglement in tensor network theory, what you have to use is this pseudo entropy. And then the notion of time-like entanglement entropy in ADS-CFT or the notion of pseudo entropy in DS-CFT are related to the pseudo entropy. So that's why we are discussing these things. Now to go back to so until now I have talked about like quantum many body system, but what will happen if we go to quantum field theory. So in quantum field theory, so what you can do, you can start with a lattice system or quantum many-body system. So like this. So you have this, and then you can define a region A, so consist of many points, and then B, which is the complement of this region. Then you can factorize the full Hilbert space as points. So for every point, you can define a Hilbert space, and then you can take simply that Hilbert space of A is basically product of all the points included in BA, and for Hilbert space of B, all the points that are in B. So you can, by this construction, you can define the Hilbert space for A and B, and then what you do after that, you can take the epsilon going to 0 limit. So the spacing between these 2 points are epsilon, and you can take it 0, that it will become a continuum. So from quantum many-body to it will become a quantum field theory. So that's what I'm saying. So in this process, what will happen, that you will get a subregion which is a special region, and you can factorize the full Hilbert space as Hj cross Hb for quantum field theory from the lattice system. So this is the construction for going from many bodies to continuous limit to QFT. But then question is, if you can separate the Hilbert space, can you always define the density matrix or define the entanglement entropy? The answer is it's very difficult, because you know that in quantum field theory the degrees of freedom are infinite. So you have infinite number of degrees of freedom. So the Hilbert space is infinite dimension. So if your Hilbert space is infinite dimensional, then you cannot simply take diagonalize the full Hilbert space, right? Like the density matrix. So it's very difficult to diagonalize the density matrix in continuous limit. And one more thing is that it's very difficult to find a closed form expression for this density matrix. And other more thing is to take log of this quantity. So if it is infinite dimensional, then it's very difficult to take log of this thing. So due to this many problems, it's very difficult to do quantum field theory calculation of entanglement entropy. So what we do, we use the replica trick. So I will talk about what is this replica trick. So basically, instead of taking log of rho A, you have to define a harder problem or simpler problem, let's say, taking trace of rho A but to the power n. Why it is simple, I will come here. So in quantum field theory, you calculate density matrix using path integral. So basically, this is a diagram of a density matrix calculation of pathing. So here at tau equal to 0 or t equal to 0, you can define a subsystem A. And then when you want to define the reduced transition matrix or reduced density matrix, you simply trace over the other part. So once you trace over the other part, you have to do the gluing between the endpoints. So here you can see that I have glued the component, but I have only open cut at A. So this is the construction. So start with tau equal to 0, you can take a subregion, and then you have the same subregion here, but you have two different boundary conditions. But when you trace over A, you basically sum over all possible boundary conditions on A bar. Once you do that, you are only left with subregion A. So this is the reduced density matrix. And then for the replica trick, you basically glue them. So you take n copies of this one. So you take n copies of this and glue like a cyclical glue. So you take one endpoint of A and glue with the other parts like this. So Ij, Jk, Kl like this cyclically. Once you do that, so you have what you have done basically, you have created a Riemann surface with n sheet. So you have n sheet and you have a Riemann surface but glued at the subregion A. And then it's basically calculating of entanglement entropy is simply calculating the partition function for this n-sheeted Riemann sphere. And once you do that, you can take n going to one limit to go back to your original calculation of entanglement entropy. So this is the process how we do calculation of entanglement entropy in QFT. Right. So, but there is still limitation of this process because it only works for very symmetric cases like 2D CFTs. But if you go to higher dimension, it's very complicated and it's very hard to do this replica, and some cases it's even impossible to do. So the solution for these things are holography. So in holography, we know that the CFT or quantum field theory is related by a dictionary, what is called this ADS CFT dictionary, that to a gravitational theory. And then what is following that quantum information becomes a geometrical property in the bulk or in the holography. So many people know about this, so I will go very quickly. So in ADS CFT, basically you have a bulk ADS gravity or quantum gravity with strings, and then in the boundary you have a conformal field theory. So this is the boundary are going to infinity. This is the conformal field theory. And then you have this dictionary, which is called the GKPW dictionary, where the partition function of the boundary is related to the partition function of the bulk with this dictionary. And basically, when you take strong coupling limit, means the classical gravity, so your gravity is classical and your quantum field theory is highly quantum mechanical, then you can write it as simply the exponential of the gravitational action. So the partition function of the conformal field theory is this. So basically the geometry which is classical in the bulk become highly quantum mechanical system in the CFT side. And using this, one can calculate the holographic entanglement entropy. That is the Rui-Takanabe conjecture, that the entanglement entropy for a subregion A in the CFT is nothing but a 4-dimension 2 extremal surface in the bulk. So this is the property. The thing is that this 4-dimension 2 surface sigma A have to be homologous to the boundary A, and it have to be a minimal hypersurface. So it is 4-dimension 2, so 2-dimensionless and minimal. And then later, Lokovich-Mandelstam have proved this conjecture that if you use the replica construction, but in the bulk, means in the gravity side, you can prove that this is the case, that if you want it to be an extremal surface, it will have to be a 4-dimension 2 surface given by the area of this 4-dimension 2 extremal surface. Right. Now I will come to the main thing of our discussion, that is de Sitter CFT. So we know that our universe is expanding and it's a cosmological universe. So the simplest example of cosmological expanding universe is de Sitter space. But we still don't know what is the quantum gravitational aspect of this de Sitter space, or let's say how holography works in this universe. So for this, like in 2001, Strominger first gave proposal of DSCFT, where he said that the bulk de Sitter space has a dual in the future infinity given by Euclidean CFT. So instead of a Lorentzian CFT in the bulk, and instead of radial infinity, you have a boundary at future infinity. So in the time direction. So if you see, this is the like a Penrose diagram of the de Sitter space. So this is the past conformal infinity. This is the future infinity. And what he said is that you have a conformal field theory here, but this is a space-like boundary, so it's a Euclidean CFT. And how we have defined this thing, so you see, to say that you have a like a dictionary, we have to prepare some state. So to prepare some state, we have used this what is called the Hartley-Hawking state preparation. So you basically take tau equal to 0 surface, so in the middle of the de Sitter space, and you Euclideanize the half space. Why you Euclideanize? Because if you Euclideanize, you can do path integral and you can prepare an initial state in tau equal to 0. So this is called no boundary proposal of like a Hartley-Hawking state. And then you can evolve in Lorentzian time and go to future infinity to the conformal boundary. So this is the preparation. And you can see that the Killing vector which generates time-like translation in the bulk become a space-like Killing vector in the boundary. So that's why in boundary you don't have any time. So this is Euclidean. And in this dictionary, basically the partition function of CFT is no longer the partition function of the bulk, but it is the wave function of the bulk. So at tau equal to 0, as I am saying, this is like a Euclidean sphere. you have to path integral here, and you will get a state which is the 5 years, which is the Hartley-Hawking state, and that is related to the partition function of your CFT in the boundary, which is a SD surface. And so for this construction, you need this global geometry, and then we quoted here to get the Euclidean part. So basically, the whole de Sitter CFT geometry is that you have a Lorentzian section, and then for the half space, you have a Euclidean hemisphere glued together at tau equal to 2. So this is the setup we will take. Okay. So in this setup, as I am saying that the conformal field theory at the boundary is Euclidean and also non-unitary because there is no time there. So then you can ask like how to define a density matrix or transition matrix in this case, because if you see your CFT is on a sphere, and if you take path integral in this part, and if you take path integral in this part, because you are taking a subregion at it's some constant Euclidean slice, this is subregion, and you prepare a state here and you prepare a state here. So in DSCFT, as the CFT is non-unitary, its action can be complex. Because of its action can be complex, you see there is a I there. So in general, when you take path integral in this lower hemisphere and path integral in the upper hemisphere, you get two different states. You get phi and psi. So that's why when you get two different states, the natural notion is to define pseudoentropy instead of defining entanglement entropy, because you no longer have the same state. So that's why we use pseudoentropy to do quantum information measure in de Sitter space, as your CFT is non-unitary, come with a complex axiom. So that's why the holographic description of this pseudoentropy is similar to entanglement entropy, where you take codimension to extremal surface divided by Rg, but with a caveat. Your extremal surface is no longer a single surface, it's a joint between two surfaces. One is space time-like and other is space-like. Why is that? Because as this is the geometry of de Sitter, when you go to the bulk, this is the time direction. So if you want to build a RT surface or the geodesy, you have to go along time direction. So that's why it's become time-like. And then in the Euclidean section, this green line, it is a Euclidean section. So there is no time. So that's become space-like. So basically, your whole RT surface is a joint between a space-like and time-like RT surface, joint smoothly at this junction, tau equal to 0. And that's why it can be complex, because you know when you take like measure a time-like geodesy, the length of a time-like geodesy, it can become complex. Okay, so now we will use this RT surface proposal of this Doi-Harper paper for a spherical subregion. So we'll take a spherical subregion of ball, so like this. So this is a spherical subregion, and then we'll ask what is the codimension to RT surface to calculate the entanglement entropy, or sorry, the pseudoentropy for this DSCFT. So this is our subregion A, like a ball, and we are taking a theta equal to 0, or constant hypersurface. So then this extremal surface has two things. One is the time-like part, which is given by this yellow thing, and then this space-like part, which is given by this blue hemisphere. And these are the equation for these two hypersurface. So the time-like hypersurface given by this equation, and space-like hypersurface given by this equation. So once you have these two RT surface equation, you can basically calculate the area of these two hypersurface. And once you calculate the area, you can divide by 4G to calculate the entropy. We have done that, and if you see, then for odd dimension and even dimension, the behavior is little different. So you have some divergent species. So this delta is the UV cutoff, and then you have this H, which is the characteristic length scale, and then you have a universal part that is cutoff independent. So it does not depend on the cutoff. Whatever is your delta, it will always be there. And you see, for the odd even dimension, you have a log divergence. So this is similar to entanglement entropy. but with an extra I pi by 2 because of the weak rotation of the intervals. So this is the pseudoentropy for a spherical region in DSCFT. And you can see that this holographic pseudoentropy is UV divergent because as you go to the conformal boundary, time goes to infinity. So if you have an infinite volume of this space. And one more important thing is that for this universal part, which is cutoff independent, carries some information about the conformal field theory living in the boundary. So we have found that in case of spherical region, it is given by this universal part gives the complex central charge of the CFT given by this formula. So it's like Brown-Henoch central charge, but for d theta instead of ADS, because in ADS there is no this factor of I to the power d minus 1. You have only this part. So what you see is basically kind of weak rotation of ADS central charge for the d theta case. Now what we want to do is to do shape deformation of the spherical region. Why it is important? Because if you do shape deformation, you see that in ADS CFT, when you do shape deformation, you get some universal information of your d theta CFT. So if you see for a n ball, means a ball of nth dimension, the leading order correction to the shape deformation is order epsilon square. That means that the sphere or the ball is a local minimum or local extrema. This is given by Messe formula. And the leading order correction is controlled by the coefficient of the 2-point function of stress tensor, which is also a kind of a central charge or the quantum field theoretic quantity of CFT. So that's why it is very important to understand the shape deformation of a spherical subregion. So what we basically want to do, we want to extend this ADS CFT calculation to DS CFT or for the pseudoentropy and to test whether the analytical continuation from ADS to DS still hold for the deformation. Because we have shown that for spherical region, the analytical continuation hold. The central charge is basically the analytical continuation of ADS. We want to see whether this CT, the 2-point coefficient of stress tensor, is still analytically continued in this case. So what we have done, we have basically deformed our subregion. So this shaded part is basically our deformation. So this dashed part was our initial subregion, which was a spherical subregion, and we have deformed it harmonically using this deformation. Here you see this is pi by 2 because in global patch, sphere of unit radius in Poincare patch is basically a constant T naught equal to pi by 2 in global patch. So that's why we have T equal to pi by 2, and then we have deformed it with a parameter epsilon, small parameter, and with a harmonic deformation. So like sine function or cos function, this kind of deformation. And then we want to see what will be the holographic dual or what will be the extremal RT surface for this case. And we have seen that the codimension 2 embedding is basically given by this part which was like in the boundary but with the bulk component coming up. So you see initially we had only this part. There is no bulk dependence because it was in the boundary. But in codimension 2, we have this extra TL tau and TEL tau, which are related to going into the codimension 2 bulk dimension. So I have an image of this to understand this. So basically you see you have two, one is this time-like part and other is the space-like part. So this first one, the tau dependence is for the green part, for the yellow part, the time-like part, and this Euclidean part is for the space-like RT surface. And then you ask the following, that this is my embedding. I want to get an extremal surface which have all the properties of a RT surface. So you first ask for extremality, that is the stress of the extrinsic curvature is 0. So that will give you some constant. And then you ask two constant more. One is the boundary condition that you are not changing the radius. So this was your radius. Let's say this was. And you are not changing, so you are not changing r equal to 1. So this is one boundary condition. And the other boundary condition is that at the junction, this junction where you are gluing to space-time, it is smooth and it is like analytic. So you want that the derivative and so the function should have smooth, so it will be continuous and its derivative should also be continuous. If you impose this all this condition, then you can solve it analytically, the PL and TEL. So basically you will get these two complicated function. For the time-like case, this is given by this, and for the space-like case, this is given by this. I have just put it here to show you that these are the solution at the end. So once you get this solution, you basically found the RT surface equation, and at the end, what is only remained is the calculation of area of this RT surface. So once you do that, so these are the RT surface after deformation. If you see the boundary is deformed, that's why the RT surface is also deformed. It is no longer a simple hemisphere. And so the universal part after this deformation is like this. So the initial universal part was the central chart, as I have told you. But you see, when there is deformation, it is order epsilon square, so there is no first order deformation. That means it's a minimal or extremal. You know that if you take derivative of a function and you get 0, that means it is extremal. So similarly, so we see that there is no first order correction. So that is that the sphere is the extremum of this pseudoentropy. And the leading order correction, this S universal, is simply given by this complicated function. But what is important is the CT, which is the coefficient. And we have found that the CT is also the analytical continuation of this CT of ADS CFT. So for ADS CFT, there is no this one. So I to the power d minus 1, there is no I to the power d minus 1. But for DSCFT, you find that the CT is basically analytical continuation of ADS. So this is the ADS radius going to DS radius. In this process, what we have basically proved is that the shape deformation of pseudoentropy also give you a similar universal formula for pseudoentropy. Now you can ask that you have done it for Einstein gravity, will it hold for higher curvature gravity? The answer is yes. So we have gone beyond Einstein gravity. Yes, so we have gone beyond Einstein gravity. So we have taken basically a higher curvature gravity, or let's say for our case, we have taken a quadratic curvature gravity. So you have this Einstein-Hilbert part, and then you have coupling this higher curvature coupling lambda 1, lambda 2, lambda 3 with all this Riemann. And then you can see that for the de Sitter background, the higher curvature entropy function is given by this one. And once you calculate the SQG, you see that the universal part is also given by the CT of the higher curvature gravity. So for the higher curvature gravity, the only difference is that the CT is multiplied with some coefficient which is dependent on the curvature coupling. So once you take all of them to 0, it will go to Einstein curvature. Einstein CT. So that's why you see the CT of higher curvature is related to CT Einstein through the coupling coefficient. So hence we have proven that for higher curvature gravity also the structure still holds. So basically it is a universal formula. But we have gone this formula. This one is a universal formula. So for different theory, the CT could be different, but ultimately the result will be same. The structure will be same. Okay, so I am almost there. So then this is the conclusion. So we have shown that for the deformation, the contribution, the leading contribution is order epsilon square. So sphere is a local extrema, and then we have also shown that the CT of this DSCFT is basically analytical continuation of ADSCFT. And we have proved for higher curvature gravity also this equation still holds. So this formula is universal. And basically we have conjectured that if this CT what we have got for de Sitter is an analytical continuation of ADS, so maybe this should be the CT or 2-point stress tensor coefficient of this non-unitary CFT, which is dual to de Sitter space. Because in CFT, in non-unitary CFT, it's very hard to calculate the 2-point function of a stress tensor. But what we have done is basically we have used gravity or geometry to find our complicated universal information of a non-unitary CFT using the holographic dictionary. So the future direction could be to go to higher order correction. So here we have only gone to first order correction, which is order epsilon square. If you go to higher order correction, we know that in ADS-CFT it is controlled by the higher point coefficient of the stress tensor. So should we get the same for de Sitter case, we have to check this. And then for the time lag entanglement. So we know that the time lag entanglement entropy in ATS is related to pseudoentropy in TS. So whether we can do shape deformation in time lag entanglement also and get the CT of the ADS-CFT. Then two more important things. This thing I have not mentioned very much, but the validity of this prescription. So recently there are some progress on first law of pseudoentropy, whether we can get the Einstein equation from the pseudoentropy. And they have found that to do this, you have to basically complexify whole de Sitter spacetime. So if you complexify whole de Sitter spacetime, you will get the correct Einstein equation from pseudoentropy. But in our prescription, we have used the real de Sitter space. We have not used complex de Sitter space. So the next question will be, can the shape deformation result we have got should be the same result that would be got from complexification of the geometry. So we are currently working on this. We have some nice result that indicate that they should be same. The ultimate result should be same. The process could be different, but the ultimate result for CT should be same. And lastly, the renormalization of pseudoentropy. So as I have told that the pseudoentropy is divergent or infinite. So can we do renormalization of pseudoentropy, what we do in ADS-CFT, like renormalized entanglement? And this is, we have already done it using conformal renormalization technique in de Sitter in our recent paper. So these are all. So yes, so I conclude. Thanks for inviting me for the talk, and I also want to thank my collaborator, and also thanks to Pablo Bueno and Tadashi Takanagi for interesting this discussion, and thanks to the audience for giving their time. Thank you.
Are there any questions?
I have a question.
Yes.
So you mentioned when you were defining the pseudoentropy in terms of the transition of the reduced transition matrix, that of course the interpretation in terms of distillable belt pairs doesn't apply when the matrix is non-Hermitian, right? But what about in the case where the eigenvalues are negative? Because you say, so in order to have a nice interpretation in terms of distillable pairs, you require a Hermitian and a semi-positive definite. However, the example that you gave doesn't have a positive definiteness, because you can see that the product like cosine theta 1, cosine theta 2 can be either positive or negative. I agree that they're always real, but they can be either positive or negative. So in that because you were mentioning that as an example where the interpretation in terms of distillable belt pairs still holds. So what happens when the eigenvalues are negative?
I think these have to be this one have to be strictly positive.
Right. I also think so.
I think because of the probability.
Yeah. So then basically there will be regions in the space of theta 1 and theta 2 where this will have the interpretation in terms of distillable belt pairs. But not everywhere.
Yes.
Right?
There should be restriction on what should be the value of theta 1 and theta 2.
Right.
For certain values, maybe it will not be it will not pass this state.
Right.
The semi-positiveness.
I see. Okay. Good. Yeah. That's my question basically.
I have a question in the last slide for CT.
Yes.
The higher periodic corrections. Yes. Could you explain why the CT only depends on lambda? Like on the
there is dependence on AD, which is this one. So AD is like lambda 1, lambda 2, lambda. So this is the AD, right? So it's depend on all the coefficients, lambda 1, lambda 2, lambda 3. I have separated it like this because I have used AD, AR. So that's why I have separated it. Yeah. So
there is a reason for splitting it like that. Maybe you can mention.
I don't remember.
If you're not considering the formation, basically, so the AD, you can think of it kind of like as a G Newton redefinition, let's say, right? So if you're considering only the undeformed sphere, or if you're considering, for instance, let's say pure ADS or pure DS, right? Then basically the presence of the higher derivative terms just effectively changes the Newton definition by this AD. But if you have deformation, then there is more. This is the reason.
A question when lambda 1, 2, and 3. What happens if you clone the parameters in order to have the Gauss-Bonnet density? Is there any consequences because you're working like with a Polygon invariant? So what would be the contribution in that case?
It
or
will not-
having something in
The result will be same, only that you will fix this dependence, right? Lambda 1, lambda 2, lambda 3. They are related, right? In Gauss 1 and gravity, like
yes,
there are relation.
1, 4, and 1, you obtain the Gauss-Bonnet density.
Yeah. So then you will get a particular result, like you will fix lambda 1, lambda 2, lambda 3, and you will get what will be the CT for a CFT which is dual to Gauss-Bonnet gravity. So you will get a conformal field theory description of dual of Gauss-Bonnet.
I guess the question is what will happen in 4 dimensions.
Yeah, 4 dimensions.
In 4 dimensions.
Yeah.
Yeah, because it's an invariant, Polygon invariant in 4 dimensions already.
So in 4 dimensions, this will be like d equal to 3. So because this is the boundary dimension, so this is become like basically 1. Then I think this will also simplify. So because you have to put 3, so ultimately you will get some simple equation. I don't remember what it will be, but it will be like some simple equation.
Okay.
But the point is that in 4 dimensions, adding the Gauss-Bonnet doesn't change the theory. So you will still have this feature.
Yes.
Yeah. So it's just so
it will be a multiplied to the Einstein coefficient, right? Or
no. It will be exactly the Einstein coefficient.
it will be the same.
Yeah. Because so you're adding a topological invariant. You're not modifying the theory.
This should be like 1 then.
Yeah.
But adding the Gauss-Bonnet, if modify the action, modify the boundary terms.
Yes, exactly. So it modifies the boundary term, but not the not the area law.
Area law, yeah.
Oh,
Same. Because there you're calculating with the solid point of the relation of Black integral, or so
This is certain one.
Okay. Okay, got it.
Because this SQG is a extreme. After extremizing, you will get this one. So there are some extra term which is like extrinsic curvature dependent that I have not written here.
Okay.
And when you take extrinsic curvature going to 0, the trace of extrinsic curvature going to 0, those term goes to 0, which is the like extremality condition or the saddle point condition.
Okay, perfect. Okay, thank you.
What behavior would you expect for like derivatives of Riemann?
Negative?
Derivatives of Riemann?
Like
not only algebraic power.
You mean for like real higher curvature like this? I think the formula will still be the same, but the like coupling coefficient will change, right?
What will happen is that you won't have just let's say Shillong functional, right? You will have this meow's function. But we haven't done the calculation, but we expect the same entropy functional that we got for ADS to still be valid for DS.
Yes.
Like the analytical
continuation. Yes. Yeah. For the backing.
Yeah.
Right. This is for the backing.
So the analytical continuation comes here.
Yeah.
So this L star square will become minus L star square when you do analytical continuation. That's true.
There was maybe a naive question, but if you are derivatives of the Riemann or something like that, when you have like Ostrowski instabilities in the system, for instance, if you have 4 derivative terms, you will have like some Ostrowski instabilities. I don't know what will happen with the entropy in that case.
I have no idea, but yeah.
Yeah, it works.
It's a good question. So this will modify the dynamics of the gravity theory, right? It will make it unstable, like you know. But the point is that we're just looking at the vacuum state. So this is the pure de Sitter bulk, right? Which always exists, just like in ADS, right? Like for any higher curvature gravity, always needs a pure ADS or pure DS. In our case, pure DS bulk. right? And this is the vacuum state of the CFT. But the CFT may be ill-defined. Like the dual CFT may be ill-defined if it has this instability in the bulk. But assuming that it exists, the pure de Sitter is always a bulk solution.
Okay, perfect. Well, correct me if I'm wrong, but I think if you have like these instabilities, you can have a degenerate vacuum in that case.
Yeah, sure. You can, but then you have to choose a branch.
Okay, you choose a branch and you. Okay.
Yeah. So usually the branch that is chosen is the one that is connected to Einstein-Hilbert, let's say. So if you start like Einstein-Hilbert plus curvature couplings, there will be one of them that will be connected to the Einstein-Hilbert branch.
Only one or more than one? You know.
There is only one that is connected to the Einstein-Hilbert branch, but that one may appear with a multiple with a algebraic multiplicity higher than one. But it's still one branch basically.
Okay, perfect. Okay.
Yeah.
Thank you.
Is there no questions? We thank again. I will have a copy ready of time.
What's up? The sun.
One more than you, that I was.